Hello and welcome to Acoustics 2. This is the second of two programs covering acoustics. In part 1 we discussed how manufacturers test and rate air distribution devices such as terminal units and diffusers for acoustical performance. After a brief review, we'll move forward and look at the various criteria used to describe room sound levels and provide advice regarding the best practices when writing acoustical specifications. We'll also cover the effects of lining materials and provide installation techniques necessary to achieve good acoustical performance. My name is Randy Zimmerman and I'll be presenting today's program. I'll be joined later by Jim Oswegen and David Pick for the question and answer portion of today's program. Jim is the chief engineer at Titus with 47 years of HVAC experience, and David comes to Titus with over 15 years of experience as a consulting engineer. You may submit your questions at any time during the webcast, and we'll answer them for the benefit of all at the conclusion. After a brief recap of what we learned in Acoustics 1, we'll discuss the limitations of NC-based specifications. We'll also talk about acoustic quality and a different noise criteria called RC. We'll look at recommended installation techniques for terminal units and air outlets and see how lining materials also affect acoustical performance. So to recap, we can't measure sound power directly. It can only be determined in comparison to a reference sound power source. We test products like terminal units and air outlets in reverberation chambers because they provide an ideal environment of high isolation from background noise as well as low absorption. This is necessary in order to accurately measure the low rumbling, hissing, and humming noises produced by these products. When NC levels are chosen as the basis of design, they should match the purpose of the room in order to create appropriate acoustical environments. As we learned in part 1, sometimes a room that's too quiet can be just as much of a problem as a room that's too loud. In shared workspaces, higher background sound levels can result in a more productive work environments. All manufacturers test terminal units and air outlets to AHRI standards and then publish the performance ratings in accordance with AHRI standards. AHRI standard 885 provides standard assumptions that all manufacturers should use to estimate NC levels for catalog data. These same assumptions should be used as the defaults in selection software as well. It's always important to remember that your actual job site conditions may or may not match these assumptions. Your ceilings could be better or worse, or you may not have a ceiling at all. Extra care must therefore be taken when estimating sound levels in spaces other than standard office environments. So now let's move on to some new topics. Many project specifications that I review include scheduled maximum allowable NC levels for various products without any information regarding the sound paths. Now it's impossible to know whether a product can meet such a requirement with so little information provided. We refer to such an unqualified NC level as an open spec because it leaves the door open for misinformation and misrepresentation. An unscrupulous vendor could say that they can meet the spec requirements because under some circumstances they might. For instance, a fan-powered terminal supplying air to a warehouse full of pillows. Now obviously, that wouldn't be very honest to make such an assumption. Unfortunately, many people in our industry won't ask questions when faced with too little information. It's often simpler to throw out a number rather than stir up a debate. Although it would be much better to include sound path attenuation that all vendors should consider, the very best approach is to set maximum allowable sound power levels that all vendors must meet. This simplifies the submittal process for all parties and eliminates any guesswork. This is by far the best way to ensure that acoustical design goals are going to be met. Manufacturers must produce performance data that meets industry standards and will be useful to engineers and designers. If a diffuser is tested in a reverberant chamber, the sound pressure will be measured and the room absorption will be added to calculate the sound power at a given flow condition. If that sound power were plotted on an NC chart, it would look like the upper red line. According to the chart, the best sound level is in the 1000 Hz or 5th octave band, making it the critical band that sets the overall sound level of NC 40. Now this would be a misuse of an NC chart because NC charts are used to plot sound pressure, not sound power versus frequency by octave band. Remember, sound pressure is sound power minus room effect or room attenuation. Every environment includes some amount of attenuation or absorption, so we never really hear the full sound power of a device. According to AHRI standard 885, manufacturers are to assume a 10 dB room absorption in each octave band when presenting catalog data for air outlets. This is meant to approximate the room effect of a standard office with a lay-in ceiling, commercial carpet, and some furnishings. If we make this standard 10 dB deduction, we find that our product now produces an NC 30 sound level, and that's how it would appear in most manufacturers' catalogs. It's important to understand that products applied in spaces with harder surfaces and less absorption will likely be louder than sound levels shown in catalogs. For this reason, sound power should be used when estimating sound levels for spaces other than typical offices. Now let's look at a more typical use of an NC chart. If we want to know the sound level of a room served by a fan-powered terminal, we would enter the room, close the door, and take octave band sound pressure readings using a linear sound meter with octave band filtering. We would then plot the results on an NC chart. The result would look like the red line in this chart. It's a rather ugly spectrum because it shows a rather large spike in the 125 Hz or 2nd octave band. This is a common characteristic of fractional horsepower motors turning forward curved blower wheels. They typically create their highest sound level in the 125 Hz band, but sometimes it can shift into the 250 Hz band as fan speed is increased. So in this case, we would say the room is NC 45. Obviously, the 2nd octave band is the critical band that sets the NC level for the space. The higher frequencies just trail off and are of little consequence. Any manufacturer developing a fan-powered product knows that the lower the sound level is in the 2nd octave band, the better the product will be. By the way, if you're interested in taking sound measurements but don't own a portable sound meter, you might be surprised to know there are apps available that can turn your smartphone into a reasonably accurate sound meter for just $1 or $2. That's truly a miracle of technology, considering that 20 years ago, even the least expensive portable sound meter cost upwards of $15,000. This example illustrates one of the shortcomings of using the NC rating method. If we stood in a hallway and measured the room sound pressure near a sidewall grill, it would look like the red plot. We would say it's NC 35 and the critical band is in the 1000 Hz or 5th octave band. This is very typical for grills and diffusers. If we moved to a location outside a mechanical closet and took a second set of sound pressure readings while the air handler is running, it would look like the blue plot. We would say that it's NC 35 and being set in the 125 Hz or 2nd octave band. You'll notice that instead of the ugly spike we saw in our fan-powered example, the air handler produces only a bump in the same band. Larger fans produce much smoother sound spectrums, but they still typically peak in the 125 Hz band. So this brings up a very important question. What does NC 35 really sound like? Does it sound like a grill? Does it sound like an air handler? Nobody really knows what NC 35 sounds like. A grill is making a hissing noise, and the air handler is making a rumbly noise. If we specify that an executive office shall not exceed NC 35, will it sound like there's a grill in the office, or will it sound like it's next door to an air handler? They're both NC 35, but they sound nothing alike. This is the problem with NC. It only sets a maximum loudness, but provides no clues about sound quality. So what does NC 35 sound like? The answer is no one really knows. I like to explain that there are an infinite number of NC 35s and they all sound quite different. They range from a very rumbly NC35 that's all low frequency, to a nice balanced NC35 in the center, to a very hissy NC35 that's all high frequency. While we know that everyone would prefer the nice balanced NC35 in the middle, there's no way to guarantee this by specifying in terms of NC. So NC ratings provide limits on overall loudness or speech interference, but the lowest octave band is centered on 63 Hz, so it doesn't cover some low frequencies that are very important to acousticians. Room criteria, or RC, addresses this shortcoming with two additional octave bands centered on 31.5 and 16 Hz. More importantly, RC also provides an indicator of acoustic quality. Room criteria, or RC curves, have a lot in common with NC charts. They both have sound pressure on the vertical axis and octave bands on the bottom axis, but you'll see that RC adds two extra octave bands to the low frequency end of the scale. Like NC curves, the RC curves are in increments of 5, but instead of sweeping curves, the RC curves are straight lines. There are also two shaded areas called Region A and Region B up near the top. I've heard them called Region Bad and Region Awful. Any plotted data falling in either of these regions indicates a likelihood that low frequency noise could cause physical vibration in a building. When speaking in terms of room criteria, or RC, it's important to say RC followed by a number followed by a letter. We can't just say RC40. The number is similar to an NC value and is often within a few points because it signifies the speech interference level or the overall loudness of the room. The letter is a descriptor of sound quality, and the RC value is incomplete without it. An N signifies a neutral sound spectrum. This is generally thought of as a pleasant balanced spectrum. R signifies a rumbly spectrum and generally indicates a low frequency imbalance. H signifies a hissy spectrum that's defined by a high frequency imbalance. If the R spectrum gets too rumbly, a V is added to signify possible physical vibration, and it then becomes an RV for rumble with vibration. It's easy to calculate the speech interference level of your RC. We simply average the sound pressure values measured in the speech interference bands. These are the 4th, 5th, and 6th octave bands. Coming up with the letter is a little bit more involved. We're going to run through some graphical examples, but it's important to know that many software tools exist for determining NC and RC results from octave band sound pressure data. Since RC is going to provide an indicator of tonal quality, we need to look at imbalances in both high and low frequency to determine what sort of spectrum we have. If the sound pressure in any low frequency octave band is more than 5 decibels higher than the speech interference level, the spectrum indicates rumble. If the sound pressure in any high frequency octave band is more than 3 decibels higher than the speech interference level, the spectrum indicates hiss. If no imbalances are found, we know that we found a nice balanced neutral spectrum. So let's look at some examples. In this example, we average the speech interference bands and come up with a 34. We look at the offsets and find that we have 2 points falling outside the allowable low frequency offset. This tells us that we have an RC34R indicating rumble. In this example, we average the speech interference bands and come up with a 33. We look at the offsets and find that we not only have points falling outside the allowable low frequency offset, they're all the way up into region A. This tells us that we have an RC33RV indicating rumble with vibration. In this example, we average the speech interference bands and come up with a 34. We look at the offsets and we find that we have no points falling outside either of the offsets. This tells us that we have an RC34N indicating a neutral spectrum. As you can see, neutral spectrums are very flat and nearly linear. In this last example, we average the speech interference bands and come up with a 35. We look at the offsets and find that we have points falling outside the allowable high frequency offset. This tells us that we have an RC35H indicating hiss. It's rare to see any manufacturer's catalogs referencing RC, so exactly who's using it? Acousticians like to use RC to explain why a sound environment that meets a specified NC level may be objectionable to an occupant. After the NC has been verified, it's common to see an RC analysis used to explain the nature of the problem along with suggested solutions. Don't expect to see NC levels disappearing from manufacturers' catalogs. NC remains the preferred method of equipment selection. Now we'll take a look at variables that can affect the acoustical performance of terminal units, such as installation, optional attenuators, and liner types. When discussing the acoustical performance of fan-powered terminal units, radiated sound is usually the main concern. Fan-powered products typically generate low-frequency noise in the second and third octave bands. This low-frequency noise is difficult to attenuate because the wavelength is long. Unfortunately, this low-frequency noise tends to pass through ceiling tiles. Ceiling tiles do a good job of blocking high-frequency noise, but are acoustically transparent to low-frequency noise. Non-fan terminal units have a single noise source called a damper. Properly sized dampers rarely present a noise issue in installations where ductwork is internally lined. In the interest of improved indoor air quality, many buildings are now being designed without exposed lining materials inside the ductwork. When that's the case, extra care must be taken when sizing and selecting products to prevent discharge noise problems. This drawing depicts an ideal terminal unit installation. The duct approach should include at least 3 equivalent duct diameters of straight duct. The inlet should be sized for a maximum inlet velocity of 2,000 feet per minute. The unit should be located as high above the ceiling as possible, usually right up against the ceiling slab. If at all possible, there should be a ceiling. Although low-frequency noise passes through typical suspended ceilings, they're very effective for blocking high-frequency noise. Flexible inlet and discharge connections are recommended, especially on fan-powered units, to limit duct vibration. Although isolators are not required on unit hangers, they do provide extra insurance against vibration. A discharge duct should be lined if at all possible and should be sized for a maximum discharge velocity of 1,000 feet per minute. The first diffuser takeoff should be no closer than 4 or 5 feet from the discharge of a fan-powered unit. 3 to 5 feet of flex duct can attenuate a considerable amount of discharge sound. Single duct attenuators are typically just line duct sections that provide the same noise reduction that one would expect from line ductwork. The effectiveness of such an attenuator is largely determined by the type of lining specified. Dual duct terminals are available with optional mixer attenuators, but the main purpose is to create the turbulence necessary to force the hot and cold air streams together. For this reason, they provide minimal sound attenuation. Fan-powered terminals are often available with optional induced air inlet attenuators. Many contractors refer to these devices as boots. They often look like a lined steel box with one side missing. They usually block the line of sight to the blower and force the induced air to turn a corner when drawn into the unit. At best, these boots or lined elbows may reduce the radiated sound by 1 or 2 decibels in the critical octave bands. More carefully designed and constructed attenuators, however, can provide far better results. There are some general rules regarding the effects of liners on terminal unit acoustics. In a standard single duct terminal, the choice of liner has little or no effect on discharge sound because the units are short and the airstream doesn't really contact the liner. The softer the surface of the liner is, the more absorptive it'll be. This tends to create lower discharge sound levels. The harder the surface of a liner is, the less absorptive it'll be. This tends to create higher discharge sound levels, but it can also add transmission loss to the casing, resulting in lower radiated sound levels. In fan-powered units, dual-wall construction can make radiated sound levels harder to accurately predict. The high transmission loss can create a directional sound that exits through the induction port. In large open plenums, this would likely not be an issue, but in confined ceiling spaces it can cause problems. In the case of fan-powered terminals with dual-wall construction, AHRI 885 will generally predict higher sound levels than those that will be actually heard due to the directionality of the sound. And don't forget about flex duct. When flex duct is properly installed and managed, it can make a major reduction in discharge sound levels. The important thing to remember is it should be no more than 3 to 5 feet long and should be properly supported to create a proper inlet condition for the grill or diffuser being supplied. Just because it comes in long pieces doesn't mean you have to use the whole thing. They do make tools for cutting flex duct, so there's no need to tie it up in a knot and shove it above the ceiling. Unfortunately, not all installing contractors are aware of these facts. Here is an example of an ideal inlet condition per AHRI. Obviously, nobody has room to duct the diffuser this way, but this is an approved testing arrangement, and it helps explain why manufacturers use the test plenum method to simplify the test setup and eliminate duct-related issues when testing air outlets. Here's an ideal flex duct installation with a smooth radius approaching a straight drop to the diffuser neck. While it's true that even an ideal flex installation can add an NC point to the sound of a diffuser, it's more important to understand that it can eliminate a great deal more of the sound from the air handler or terminal unit supplying air to the diffuser. So flex duct still provides a net benefit. Here's a more typical flex installation that creates a long radius to the diffuser neck. This would likely adversely affect the air pattern of the diffuser by putting more air out one side, as well as adding 3 NC points to the diffuser sound. Here's a situation where the flex duct is a little too short, resulting in an abrupt turn into the diffuser neck. This could easily add 5 NC points and would most certainly affect the air pattern of the diffuser. Although this installation doesn't look bad, it's actually the worst. The flex duct goes beyond the diffuser neck and has to angle back. This sort of curvature causes the air to tumble in the flex and could add 7 to 9 NC of noise to the diffuser. So even the best flexed installation may add a little noise to the diffuser, but it can be a net improvement due to the sound reduction it provides upstream. Certain diffusers are more susceptible to inlet condition effects due to their design. Typically, a plaque or perforated diffuser would have the most issues, while multi-cone or louvered diffusers would have the least. That's because the cones or louvers tend to better redistribute the air downstream from a poor inlet condition. Plaque diffusers can't do this, so proper inlet conditions are absolutely necessary to achieving the high performance that these diffusers are known for. And don't forget that the catalog NC values are based on a 10 dB across-the-board deduction that may not reflect your actual job site conditions. Just because manufacturers offer neck-mounted balancing dampers doesn't mean you should use them. A damper on the neck of a diffuser can drastically affect the performance even in a full open position. Balancing dampers should only be located on the neck when there's no other alternative. For additional information on HVAC acoustics, there are several excellent resources available. Both the AHRI Fundamentals and Application Handbooks include chapters on acoustics. Mark Schaefer has also written a book that is available through the AHRI bookstore that provides lots of practical information regarding noise and vibration control for HVAC systems based on both AHRI research and his many years of practical field experience. These are all good reference books. So, in summary, we can say that NC remains the preferred method of equipment selection, while RC remains a favored analysis method. Acoustical specifications are clearest when maximum allowable sound power levels are provided. Don't forget about lining materials and how they may impact the overall acoustical performance of a product or system. In order to avoid expensive remedial work, care must be taken when selecting and installing any HVAC equipment. Well, that concludes our program for today. We thank you for spending this time with us and hope this material will benefit you in your professional endeavors. We will continue to produce more programs covering other HVAC topics and hope that you will join us. Our panel will now begin answering questions that came in during the program. If you have any questions, please enter them in the box on the right side of your screen. We'll take questions now.